So in the last video, we saw how calculating certain particular integrals translate to calculating some given areas. So as an example, here we have the 60a minus 6x squared, which is going to have the area given by the integral from 0 to 10 and here of the function. And if we get the antiderivative, then we get to calculate this corresponding area. Similarly, on the next example, we had the square root of x, and we were calculating all this area with the integral from 4 to 16 of 3 square root of x. Here we get a full positive area. In the case of the sine of the 3 sine of x, when we calculated the integral from 0 to 2 pi of 3 sine of x, the net area was 0. And that was something that we can see both from having a positive area that is equal to the negative area, or from calculating the antiderivative and making sure that that integral is 0. In the last scenario, we had the square root of t minus 1 divided by t. And in that situation, we had that we have this negative area going on. And when we obtain the integral, then we were obtaining a corresponding value. Now, another example of this is what happens if we have f of x equals 6x times x plus 1 times x minus 2. So notice in this case, we have a function that is going to have 3 zeros, 1 and minus 1, 1 and 0, 1 and 2. And we want to see the difference between the net area and the area itself between minus 1 and 2. Now, as you can see on this particular scenario, we can describe the function of area as the integral from minus 1 up to a certain point. And depending on whatever that point is going to be, then we're going to have positive areas up to from minus 1 to 0. Then we're going to have areas that is going to start to be negative from 0 onwards up to a certain point. And then very likely when we're past 1, the negative area that we're going to have for integrals is going to be bigger than the positive, and the overall term of this is going to be a negative value. So let's actually see that example here. So let's consider the full integral from minus 1 to 2 of the function 6x x plus 1 x minus 2 dx. As it's easier to calculate an integral when we multiply this, we're going to do 6x times whatever the multiplication of this is, which is x squared minus 2x plus x minus 2. And then we're going to multiply by this over here. Notice that this becomes x squared minus x minus 2. So this is going to become at the end 6x cubed minus 6x squared minus 12x. Now at this point, by the rules of the fundamental calculus theorem, what I'm going to do is I'm going to calculate directly on the antiderivative, and I'm going to later plug the points over here. So the way that I can do this is I'm going to calculate the antiderivative here right now. This is going to be 6x to the 4 over 4 minus 6x cubed over 3 minus 12x squared over 2. And then instead of putting the full function and going to plug here, I'm going to say directly that these values are going to be between minus 1 and 2. So I'm going to use this bar to represent that. And of course, then later, since this is the function f, I'm going to do f of 2 minus f of minus 1. So let's do that now here. This is going to be 6, 2 to the 4 over 4, minus 6, 2 to the 3 over 3, minus 6, 2 square, and then we're gonna get rid of this c right away. We're gonna plug into the minus 1 to the 4, 6 over 3 minus 1 cube, and minus 6 minus 1 square. Okay, simplifying these values, so 2 to the 4 is 16 divided by 4 is going to be 4. So this first value is going to be 24. Now 2 to the 3 is 8. 8 by 3 is 48. Or if I simplify this 6 by 3 with a 2, I can instead do a 16 over here. And 24 over here. 6 by 4. Now minus 6 over 4 can be simplified to 3 halves, and this minus 1 to the 4 is just minus 1. 6 with 3 is 2, and with this minus to the cube, which is minus 1, we're going to get a plus here, and we get finally a minus 6 going on in here. Now that means that from the first value we're just going to get a minus 16, and we get a minus 3 halves over here. This is going to give me a minus 4, so I get a plus 4 over here, and the final result is going to give me a minus 3 half minus 12, or minus 27 over 2. Okay, so notice that we don't necessarily have to go over the whole ordeal of defining the full function for the antiderivative. We can use, now that we know that we can use the fundamental calculus theorem, calculate the antiderivative, put it between the two limits of integration, and plug the limits of integration. Now let's generalize this with this behavior with areas. So consider the function that we have here. We have a some sort of sine function where we're getting an oscillating behavior, and so we have different regions going up and down until we get up to 16. So we can talk about the zeros of the area in 0, 17, and also the point where the area is going to have the maximum and the minimum. Notice that we're not talking about the function, we're talking about the area. So how that's going to be calculated? Well, first here we have area 0, then the area starts increasing until we get to this point. Then here is going to start decreasing, and when we get to this point, the area is going to become 0. Then at this point, the area is going to start increasing again positive, and then from here it decreases, and then it reaches 0. So this can be shown by writing the integral. Of course, we're going to write a of x as the integral from 0 to x of f of x f of t dt, and that's going to give me the net area itself of the graph of f and the t axis on the 0 to x interval. So pretty much this. Now the first time that we mentioned that in 0 we have area 0, remember that we can argue that by doing the function area as the integral from 0 to 0, and that's going to give me a 0 integral. So that's 0 area. Now because R1 and R2 have the same area but lies in opposite sides, then we have that the area up to 8 is 0, and that can be represented as the area of 8 is equal 0, or the integral from 0 to 8 of f of t dt is 0. Similarly, a of 16 is 0 by the same reason. We have all the positive, same thing but negatives, positive, same thing with negative, so everything cancel out, and from 0 to 16 the net area is going to be 0. Therefore, we're going to have zeros at 0, 8, and 16. Now observe that the function is going to be positive between 0 and 4, and it's going to be positive from 8 to 12. That means that the function is increasing from 0 to 4, and is going to increase from 4 to 8. In the same fashion, the function is going to decrease from 4 to 8, and it's going to decrease from 12 to 16 until it reaches 0. Notice that this is very similar to what we do with the derivative functions when we're trying to find the area. And so combining these observations here, we're going to be able to just describe how the area function looks with the function. So notice here we have the functions that we had before, and above we have the area function being graphed. And so notice here we have that is 0. It starts increasing. It reaches the peak in the point where it's 4, because this is all positive area. And from this point onwards starts decreasing, and it reaches 0 when we get to 8, because this area is equals to this area, but they're opposite. Then at this point it start going up again and increasing. And then at 12, which is where we get the peak of a new positive area, and then we transition to negative area, then the area function starts decreasing and it reaches 0 at 16. So this is just to show that with the area function, given the information from the original function, we can also get find a way to make a graph of the antiderivative function from the original function. All this, however, is coming from the behavior that we see from the area. Now, if we take a look at more details, we can describe the function a of x being the from 0 to x of f of t dt, and we can call that function the nth area over 0 to x. So when we put certain x in any point, that's going to be calculating this positive area, then this negative area, and of course, depending on where it is, then we're going to get that is positive or negative, depending on how much of each of the pieces we're taking. Now, let's see a little bit of the change on the net area with this example. So when we're going from 0 to 4, the net area is increasing, and you can see that from the behavior of the graph before. When we're going from 4 to 8, it decreases, and so we can see also that reflected in the function. From 8 to 12, we're going to have an increase again, and again from 12 to 16, we're going to have a decrease, and it reaches 0 again, remember, in 0, 8, and 16, and so that's why it reflects this particular graph area function. Now, to get away from this, let's actually use the fundamental calculus theorem on the first version. So if you recall, the first version of the fundamental calculus theorem actually states that there's a relationship of antiderivative between the functions. So for example, if I define the area of x to be 0 to x of f of x, or f of t dt, the fundamental calculus theorem says that a prime of x is actually going to be f of x. And so what is happening from here to here? Well, the procedure of the derivative is get rid of the integral, and we're essentially plugging in the x in the variable, and we're multiplying by the derivative of this function. Okay, so we really have a 1 over here. If we have something different, we can have also a definition given a different way. So let's say that you define a of x as certain constant a to a function g of x of f of t dt, then the derivative of this function will be f of, and then plug in here, f of g of x, and then we'll multiply by the derivative of this function, g prime of x. And in here, we don't have any issues because we're plugging f and a, but because a is a constant, then the derivative is 0. And so at the end, a prime of x is just f of g of x times g prime of x. So we do have a big relationship with the derivative here. Now, taking that away to a particular example, if we have something like, well, let's calculate what the derivative is for the function 1 to x of sine square of t dt. This probably is what you are thinking that it is. You remove the integral and leave the function that is inside, and you plug in the variable that is inside, which is x, and then multiply by the chain rule, which in this case is 1. So it's all done. Okay. Now let's take a look to another example. In here, notice that we have the x on the opposite direction. And so what that's going to cause is that we first plug in here, and then we plug in here. So if we plug in phi, we have that phi squared plus 1. But then we multiply by the derivative of phi, which is 0, minus, and then plug on x, which is x squared plus 1. And then the derivative of x is 1. So at the end, we're going to get minus x squared plus 1. And that is the derivative of this integral by the fundamental calculus theorem. Last but not least, we have the derivative of the integral of 0 to x squared of cosine square of x, or cosine square of t. 0 to x squared of cosine square of t dt. Okay? By the fundamental calculus theorem again, then this is just the function inside of the integral. Cosine squared, we plug in whatever we have here, x squared, and then we'll multiply by the derivative of this, which is 2x. Again, we can do it on 0, but we're not going to get nothing of that. So this is cosine squared of 0 times the derivative of 0, which is 0. And so this is just going to get cosine squared of x squared times 2x. Now, disclaimer, you can have the scenario where you're going to end up having things on both sides. So and also let me use a different notation. Let me use a of x defined as the integral of log of x up to cosine of x of the square root of x plus 1, or actually t plus 1, square root of t plus 1. Let's use a different variable, dt. Fundamental calculus theorem says that when I take the derivative, I'm going to lose the integral, and I'm going to get the square root, plug first in cosine, times the derivative of cosine, which is minus sine, and then minus, because we're going for the lower limit of integration, log of x plus 1 times the derivative of log of x, which is 1 over x. Okay. So the two relationships of the fundamental calculus theorem is, first, the derivative and the integral are opposites. So if you make the integral of a derivative, you're going to get the function, and if you take the derivative of an integral, you get the function. So also another way of checking this. So you can say you have this sort of cancellation between what these things are, and you get the original function. Okay, and also when you have the opposite, when you have derivatives of the integral, then you get back the function with a little bit of the chain rule. The last scenario is if you have that you have a definite integral where you have this information, and f of t is the general antiderivative of the function f, small f of t, then you can write this one out as f of b minus f of a, as in the examples of the previous video. Okay, and so this is the end of section 5.3. In the next chapter, we're going to see a couple more of techniques of integration related to the opposite of the product rule with derivatives.